All right. Hi there, guys. My name is Wilfrid, and I'm a senior math tutor, and I'll be covering 7 questions related to calculus and integrals today. A little backstory upon myself. I graduated from McMaster with a major in biochemistry and a minor in mathematics. And other than that, we can get right into it. Let's jump right into it. Okay, so the first question of the day, we're going to be talking about the second derivative and pertaining to y equals x ln x, okay? So when they are talking about the second derivative, so we know that the first derivative covers the rate of change of our original function y equals ln x. So the second derivative represents, or I guess graphs, the rate of change of the derivative. So the way that derivatives work is that you can infinitely derive as many times as you want until you get down to 0, I guess you can say. And each derivative represents the rate of change of the previous derivative. Okay. So the way that we write the second derivative, so I'm going to use the Newton notation for this. So if we have f of x, our first derivative would be f prime of x. Okay. We can write, or we can write like d over dx. Okay. Cool. So the second derivative, so let me just write first and second, would have f double prime of x, okay? Or a d squared of d over x, I guess you can write that too. We can keep going on and on, f triple prime, but the derivatives kind of start being less useful past like the fifth derivative. So when they ask us to find the second derivative, we're going to need to derive this function 2 times, okay? So another useful rule here is that we see here that our original function is a product of 2 functions, x and ln of x. So we're also going to use a product rule here. So the product rule suggests that, so if f prime of x, or let's say, sorry, let me write, so the product rule suggests f of x, if f of x equals f of x times g of x, then f prime of x suggests that we sum the product of f prime of x times g of x plus f of x times g prime of x, okay? So we're going to use this product rule to find our first derivative. So let's write down our question here, okay? So our original function is y x ln x, okay? So y prime would be x, let's write d of dx of x times ln x plus x times d of dx of ln x, okay? So that would equal to 1 times ln x plus x times 1 over x, okay? Cool. So if we simplify this together, we get ln x plus 1, okay? So that's y prime. So we need y double prime, okay? So y double prime would equal to 1 over x, right? Plus 1, which is just a constant. So our second derivative is 1 over x, okay? So that's the answer to our question. And yeah, so Junior Tutor also did the solution. They stated what the second derivative is, which is to differentiate 2 times the original function. And they also stated our product rule that they used to solve the first derivative. So this solution is correct. All right, cool. All right, so the next question is, what is the derivative of secant of x? So before we even begin, we know that secant of x is just the inverse, our cos inverse. So secant of x equals 1 over cos. Okay, so we're going to use this. We're going to use this form for the rest of the derivative. Okay. So another rule of derivatives is the quotient rule. which suggests that if we have a function that is the quotient of two other functions, so big f of x is the function of f of x divided by g of x, then f prime of x would equal to this formula, okay? So we'll have f prime of x times g of x minus f of x times g prime of x, okay? And that's all divided by g of x squared, all right? So this is the quotient rule, and we'll be using this to solve our derivative of secant x, okay? So let's say y equals to secant x. So y prime would equal, oops, let's write this too, x. So we see here that secant x is also the quotient of two functions. The numerator is the function of 1, and the denominator is function of cos of x. So we're going to use our quotient rule here. So it's going to be d of dx. Let me write smaller too. It's going to be d of dx of 1 times cos of x minus 1 times d of dx of cos of x, all over cos of x squared, okay? So what is this equal to? So d of dx of 1 is 0 times cos of x minus 1 times, the derivative of cosine is negative sine. So we have negative sine of x all over cos x squared, okay? Cool. So if we simplify this, all we get is sine of x over cos x squared. So let's just write this. And we can cleverly write this as the product of 1 over cos x times the sine over cos x, okay? And that equals to secant x tan x. Okay, so that's the answer to our question. So therefore, the derivative of secant x is secant x tan x. Okay, so that's the answer. So the junior tutor also did this. They stated the quotient rule, and then they correctly applied the quotient rule to find our derivative, and then they simplified and used some identities to come to the final conclusion, which is secant x tan x. So this solution is correct. Cool. All right, moving on. All right, so the next question is going to be kind of long, and it reads, find the exact length of the curve y equals root x minus x squared plus arcsine of root x, okay? So arcsine is just another way of writing sine inverse. So let me just define that now. It's just another way of writing sine inverse, okay? So given a ratio of two sides of a triangle, you can find the angle, basically, all right? So they want us to find the exact length of this curve. So we're going to be giving ourselves a formula to use to find the length of this curve. And the formula goes like this. So the length of the curve, I'm going to write it A, is the integral, definite integral between interval AB of the root of 1 plus f prime of x squared. Okay? So this is the equation or the formula for finding the exact length of a curve. Okay? So we're going to be applying this formula to finding the exact length of this very complicated curve. Okay? So first of all, we're going to need to find y prime. All right? So let's try to find y prime. So the strategy here is to treat these as separate functions first, and just to derive this function and this function. Okay? So y equals the root of x minus x squared plus the arcsine of root x. Okay? So let's derive this first part. So I'm going to let's say I'm going to label this to be 1, and I'll label this to be 2. Okay. I don't want to keep writing out everything together. Okay, so let's do 1 first. Okay. 1. So 1 is the root of x minus x squared, right? So the derivative of that, d of dx would equal to, so this is a chain rule, so we have to evaluate the outside function first, which is the root. So we're going to move the exponent down, and then minus 1 to the exponent at the top, which would give us negative 1/2. And then we're going to derive the inside, right, which is the multiplication of this. So it's 1 minus 2x, okay? So that's the derivative of that. And we're going to simplify all this together. So we'll have 1 minus 2x divided by 2 square rooted x minus x squared, okay? Cool. Let's just move down a bit. So 2. All right, so 2 is a little bit more complicated, but we're going to get through this together. So we have arc sine of root x, okay? All right, so let's put a y here too, why not? So we're going to get rid of this arc sine because it's really hard to derive arc sine. So we're going to apply the sine function to both sides. So we got sine of y equals root of x. So this is a little bit easier. And now we're going to implicitly differentiate this equation, okay? So we're going to do d of dx of sine y. And we're also going to do d of dx of root x, okay? So this is going to be a chain rule again. So we're going to have the derivative of the outside function. So it's going to be cos, because the derivative of sine is cos, so cos y times dy over dx, because the derivative of the inside function is just y prime, or dy over dx. We're going to also apply the chain rule here, so it's going to be 1 over 2 times x to the power of 1 over 2. Okay, oops. Okay, cool. So we're going to isolate for dy dx now, okay? So we isolate for dy dx. We get, so 1 over 2 times root x, and then there's also cos y. Let me just write this. All right, so we're going to get 1 over 2 times root x times cos y. Okay, so that's our dy over dx. But the problem here is whenever we implicitly differentiate, our derivative is a function of the independent variable and the dependent variable. So we want to get rid of this cos y. So we're going to use trigonometric identity here. So we know that cos squared y plus sine squared y equals 1. Okay, we know that equals 1. So we know that cos of y equals the root of 1 minus sine squared y, okay? But we know that sine squared y, well, sine y is just root x. So sine squared y would be 1 minus x. And now we're going to sub in cos here. So actually dy over dx is going to be equal to 1 over, let me just see here, 2 root x minus x squared. Let me just see if this is right here. X minus x squared, yeah, okay. So this is our derivative for our part 2. So overall, if I come back down here, so overall then, y prime of x, I guess you can say, is equal to 1 minus 2x times over 2 times root x minus x squared plus 1 over 2 times root x minus x squared. Okay, cool. And now we're going to simplify this all together, and we get 2 minus 2x. So 1 minus x over x minus x squared. You guys can go through this math by yourself. I'm just going to simplify doing all these other steps here. It's just a bunch of adding these fractions together and reducing the top and the bottom. So this is our derivative, okay? 1 minus x root x minus x squared, okay? Now we have our equation. So the length of our curve is equal to the definite integral of interval a to b of the function root 1 plus 1 minus x over root x minus x squared d of x, okay? Cool. All right, so let's recap what we did so far, okay? So to find the length of the curve, we're going to calculate the definite integral of this function. So what we did was we found the derivative of this original function by splitting it into two parts, I guess. You don't really need to split it into two parts, but I did it for, I guess, clarification purposes. And I found the derivative of both. I added it back together, simplified it, okay? But we're missing one thing. We're missing the bounds for this curve, okay? Now, normally, they would give you the interval for the bounds of this curve. They'll say, oh, find the curve, length of the curve from 0 to 4. They'll say, find the length of the curve from 1 to 100, okay? But here they didn't give us the exact length of the curve, right? So we're going to assume that the length of the curve is the entire curve, okay? So let's look at this function, right? So what is the domain of this curve, right? So we can see that this function is expressed by the addition of two square roots. So we have the square root of x minus x squared, and then we also have the arcsine of root x, okay? So we know that for a fact that square root functions cannot be, the x cannot be negative, right? So in this value, this cannot be negative, so we're already restrained to saying, okay, x minus x squared, the domain for this part of the function has to be between 0 and 1. Okay. For example, if x was 2 or 1 or greater, then this x squared will be greater than this x, and this will be a negative inside the square root, and we don't want that, right? Because the square root of a negative number is a complex number, but that is not part of our function here, okay? So between 0 and 1, we're fine. Same thing with, I guess, -1, I guess, too. So actually, for this square root, it's between -1 and 1. All right, so that's the domain for this first part of the function, if you guys are following me, okay? We still have the second part of this function, okay? So arcsine, usually the domain for this arcsine function is -1 and 1. However, the domain is restricted to 0 and 1 because of the square roots, okay? Just like our first part of the function, we cannot have our square root have a negative number, right? And so because of that, our arcsine function's domain is, again, restricted to 0 and 1. And the general rule of thumb for finding the domain is we're trying to try to find the part of the function that is most restrictive, and the part of the function that is most restrictive will dictate what the domain is. In this case, the domain for our first part of the function, root x minus x squared, domain is between -1 and 1. I think. No, it's between 0 and 1. Yes, between 0 and 1. Because if this is a negative, then it would be negative minus negative, which would be a negative. So both of these functions, both parts of these functions have a domain of 0 and 1. So now we know that the length of the curve that we're trying to find is between interval 0 and 1, which is the whole entire curve. All right? Sorry if that explanation is kind of confusing. But usually finding a domain of a curve is not this hard, but this function is very complex. But conveniently, the domain is easily interpretable and understandable, I guess. If you guys want, you guys can pause this video and you guys can check for yourself the domain for this function. And you guys can see that the domain is in fact 0 and 1. It cannot be greater than 1 or less than 0, okay? So now that we have found our interval, we can write this down. So our interval is between 0 and 1, okay? So we're going to try to find this definite integral, right, of 1 plus 1 minus x over root of x minus x squared over dx, okay? Cool. So, so there's going to be a lot of computation here. We're going to expand this term first. So we're going to try to simplify our whole function in here because it can be simplified. So if we squared both numerator and denominator, we get this. 1 minus x squared over x minus x squared root of that e of x. Okay? Which is, if we expand, we get 1 plus 1 minus 2x plus x squared over x minus x squared all over our roots. Okay? We're going to include this 1 in here, so we're going to multiply this 1 by x minus x squared, and we're going to add it into our fraction here. So we get x minus x squared plus 1 minus 2x plus x squared over x minus x squared. Okay? That's all rooted together. All right. Pen in hand. All right. So now we can simplify this quotient of functions, I guess you can say. So this would equal to square root of negative x plus 1 over x minus x squared d of x. Okay? We can keep going with this. We can factor out x at the bottom, and we can cancel out the top and the bottom here. So if we do that, we have 1 minus x over x, 1 minus x d of x, and now we get this d of x. And if we now evaluate this integral, we get, so we use our power rule here, so we have to move, so it'll be x half or 1 over 2 of 1 and 0, okay? And that equals to, we're almost there, guys, 2 root x of 1 and 0, which equals to 2 minus 0, and that equals to 2. Okay, cool. So let's recap everything, because it's a very long question. All right, so we defined the length of the curve to be the definite integral of this function here. If you guys want the proof to it, you just search in Google proof for the exact length of the curve, and you'll find it. It has to do with adding small increments of rectangles to a curve, and this is what you derive the function from that. So from that formula, we try to find our derivative. So our derivative is split into 2 parts, and we found the derivative of both, and we added it together, we simplified it. Then we had to reason the bounds for this function. So looking at the function, we had to find the domain, and conveniently, both parts of the function's domain is 0 to 1. So that means that the whole curve, the whole length of the curve is bounded from 0 to 1, and that's our interval. And by doing that, we found our definite integral by simplifying this whole complex function here and reducing it down to root of 1 over x, and then we calculated our definite integral, which gave us the value of 2. Okay? Cool. So that's what the junior tutor also did. So they came up with the value of 2 in the end, so this solution is correct. Cool. Moving on to question number 4. All right, so question number 4. Find the point on the line y equals 2x plus 3 that is closest to the origin 0, 0. Okay. So the junior tutor, they first explained to us what the distance equation is, or the distance formula. And the distance formula helps us to find the absolute magnitude, I guess, between 2 points, all right, on the Cartesian plane. Okay. So our distance formula, we're going to write it as d equals the square root of the x2 of the second point minus x1 of the first point squared plus y squared, or y2 y1 squared, and that's the square root, okay? So this is the distance formula for any 2 points on the curve where x2, y2 is 1 point and x1, y1 is another point, okay? All right, so we're going to use this distance formula to derive a new formula to relate any point of our line y to the origin. So relate the distance between any point of our line y to the origin, okay? So let's say that we're going to let xy be any points on y equals 2x plus 3, okay? So the distance from x and y to 0, 0 can be explained as d equals x minus 0 squared plus y minus 0 squared. Okay, so we're assuming that x and y is a point on y equals 2x plus 3, and the distance of that point to 0 to the origin is given by that equation. Okay, so if we simplify this, we just get root of x squared plus y squared. Okay, but since y is equal to 2x plus 3, we're going to sub that in. So we have x squared plus 2x plus 3 squared. Okay, and this is now our derived equation or function to relate any points on the curve to the origin in terms of distance. Okay, so this is our function. All right. So let's say that a point 1 and 6, or 1 and 5 on our graph, y equals 2x plus 3. Then if we plug it into here, we can find the distance between 1 and 5 and 0, 0. Okay, so this is our function. So now what we're going to do is we're going to try to find the critical points of this function. So we're going to derive this function, and we're going to try to find its critical points. And we're guaranteed that this critical point is going to give us the closest point to the origin, because if you think about this function, this function has calculates the distance between the point on the line and the origin, right? So that distance can be as large as you want, but there's only one value that can be as small as it can. So if we find the critical point on our function here, then we can find our point of the line that's closest to the origin, okay? So the critical point, again, it relates to the point on our function where the tangent of the line, or the slope of the line, or the rate of change of that line, of that function is 0, okay? So that's where we're going to find our minimum, okay? So let's derive this equation. So d of d over in terms of x is, so this is going to be a chain function, or chain rule. So we're going to do the outside function first. So that's going to be 1 over 2. I should have expanded this first, actually, too. Let me expand this and make it easier. So this is x squared plus 4x squared plus 12x plus 9, okay? Which equals to 5x squared plus 12x plus 9, okay? So this is going to be 5x squared plus 12x plus 9 with a negative 1 root negative 1.5. And then the derivative of the inside is just going to be derivative of 5x squared plus 12x plus 9, which is going to be 10x plus 12. Okay. Yeah. So now we are going to reduce this and write it out in a more interpretable form here. So we have 5x plus 6 over, oh, this should be 10. Sorry, it should be 10. I was like, I think I'm doing something wrong here. Sorry, because when you expand this, it's 10x, not 12x. Be 10, so this should be 5. Okay. And this is going to be root of 5x squared plus 10x plus 9, okay? So this should be a 10. Okay, cool. All right, so what is our critical points here? So our critical points is when d of dx equals to 0. So let me write that down here. So when d of dx equals to 0, we have, so when you're calculating a derivative that is a quotient of functions, you really only need to pay attention to the numerator, because the numerator dictates when the whole function equals to 0. Okay, because if this numerator is 0, then the whole function is 0. Okay, so we're gonna just assume, we're just gonna embrace that fact, and we're gonna find the 0 for the numerator. So 5x plus 5 equals to 0, which equals 5x negative 5, and that equals to negative 1. X equals negative 1. Okay, cool. All right, so we have found our critical point, which is x equals negative 1. At x equals negative 1 on our function, on our distance function, that's where the rate of change equals to 0. And when the rate of change equals to 0, we are guaranteed to either have a max, a min, or a saddle point, I guess you can say. So we know that is going to be a minimum value because of how our distance function relates to the line, okay? So the distance can vary infinitely in distance and magnitude, right? That's the maximum distance. But the minimum distance, there's only going to be one minimum distance that is going to be the smallest value from the line to the origin, okay? But to mathematically, and to prove this, to mathematically compute this, we'll have to use a second derivative test to prove that this is a minimum, okay, to finish with our solution, because we can't just say, oh, after we find the critical point, we reason that because of the nature of our function and what our function is graphing, that this is a minimum point. So we'll have to find our second derivative here, and we have to use a second derivative test, okay? All right, so because we have to use a second derivative test, we're going to need to derive this a second time, okay? And that's where the quotient rule comes in. So let me pan down more. We need a lot more room here. Let me just take a look at our function here too. All right, so d squared of d of dx would equal to, dang, this is going to be huge. So 5, okay, let's write this first here. So I'm going to write 5x plus 5 prime. I know that's not convention. Actually, you know, I'll just write this. 5x plus 5 times this big guy here, 5x squared plus 10x plus 9 minus d of dx of 5x squared plus 10x plus 9 times 5x plus 5. And we also have a square here, okay? So Cool. So let's derive this, I guess, for a bit. So this is going to be 5 times 5x squared plus 10x plus 9 minus 1 over 2 of 5x squared plus 10x plus 9 negative half times 5x plus 5. Okay, so this is a pretty big function. And we also have 5x squared plus 10x plus 9. Okay? All right, so we're not going to simplify this. We're just going to plug in -1 here. And we're going to find what our value here is. Okay? Okay. Let me pen down a little more too. Okay, so double derivative, or the second derivative of d of dx would equal to 5. So 5 minus 10 is 5. 4, so root 2, or 2. Okay, so 5 times -1 squared, which is just 5 minus 10 is -5, plus 9 is 4, root of 4 is 2. All right, we're going to need to plug -1 here too, which is going to be 1 over 4. Yeah, yeah. So this is also going to equal to 4, I guess. But it's also rooted, so it's going to be 2. It's on the bottom, so it's going to be minus 0. Oh, thank goodness that's 0. And this bottom one is going to be -1, 5, 4. Okay, so it's going to be 10 over 4. Hopefully I get something. Okay. Let me just see what I did wrong here. 4x squared, 10x 9, 5x squared. Okay. 6x plus 6. Okay, so I need to check this person's math, the junior tutor's math, but we got two different numbers here. They got 3 times root 2 over 2 is greater than 0, and I got 10 over 4. So I'll need to check this person's math here. 1, okay, hold on, let me calculate this first. -2, 1, 1 plus 1 is root 2. Okay, root 2. -2 plus 1, 1. Okay, that's root 2 times root 3. This is going to be 3 times -3 is 0. So this whole thing is 0. Oh, I think I know what I did wrong here. So I forgot to derive the inside function 2 here. It shouldn't matter though, because you're timesing it by 0. Okay, well, in any case, I'll try to calculate this again. But we see here that our value for x of -1 of our second derivative of our distance function is greater than 0. So now we know that it's concave up, and because it's concave up, we know that the minimum is that our x equals -1 is a minimum, okay? So let's write a concluding statement here. Since dx of -1 is greater than 0, we know that x equals -1 is a minimum. Okay, so now the final piece of the puzzle is to calculate what this is, x equals -1 is on the line. So we're just going to plug it into our equation here. So y equals 2 times -1 plus 3, and that equals to 1. So now we know that -1, 1 is the closest point to the origin. Okay. All right. So I'll recalculate this derivative again off screen, and then I'll correct the solution based on whether or not it's correct or not. Okay. So we'll say the solution is correct for now. Okay. Sorry about that, guys. All right, let's move on to the next question here. All right, so the next question reads, find the volume of the solid generated by revolving the region bounded by y equals x squared, y equals 0, and x equals 2 about the x-axis and the y-axis, okay? So the junior tutor drew out this function and where the region is bounded by. So I'll try to explain a little bit on how to calculate the solid that's generated by this. But first, we're going to graph out this function, okay? All right, so we have our x and y function, or x and y axis. So x and y. So our parabola will do by blue. So our parabola is here. Okay. Gosh. Let me make it wider. Okay. So let's say this is our parabola x squared. Y equals x squared. So the region is bounded by y equals 0. So this red line here. So y equals 0. And it's also bounded by x equals 2. So let's say that 2 is here. So it's bounded by this line, x equals 2. Okay, so this is the region that we're looking at right here. So there's going to be two different three-dimensional shapes that are generated by this region that's revolved around the x-axis and the y-axis, okay? And I'll draw both of them, right? So if we are revolving around the x-axis, okay? So if we're revolving around the x-axis, we're revolving around this one, right? So let's draw an arrow like that. And the solid that is produced from this looks like this, okay? So it looks like I guess like an ear or something. I don't know. I don't really know how to describe it, but it looks like a top that's on its side, okay? Where has, I guess it looks kind of like a horn, right? And so it's like near the origin, it expands outwards, and it keeps on expanding outwards, okay? And let me, for reference, draw out our x-axis here. So let's say that this here is the x-axis, okay? And this is our y-axis. So it's revolving around like that, okay? So if you're revolving this region around the y-axis, it'll look like this, okay? So this one's a little bit harder to draw. It looks like a spherical cone, except the outside of the cone is hollowed out, okay? So if we were to draw a spherical cone like this, and so the volume is actually found in the sides, okay? So the volume is found here, okay? So it kind of looks like a bowl, all right? And if we were to draw the y-axis for reference, the y-axis would be here, and it's revolving like this way, okay? So let me draw the revolving part too. So it's revolving this way, okay? So that's part A and part B, all right? So there's two separate equations or formulas that we can use to calculate the areas for these two kind of shapes. And these formulas are dictated by the type of rotation that the region is performing against, okay? So I also preloaded some other images for you guys to see, so it's easier for us to understand. So if you have a curve like this, and you rotate it around the x region, you get this weird looking shape, okay? If you had a curve that was rotated around the y-axis, you would get this kind of weird looking shape, okay? Cool. So the integral will calculate, if we were to calculate a definite integral of this region, we are basically calculating the area under the curve, which calculates the addition and the sum of very small rectangles of very small intervals, okay? So there's a proof and there's a derivative that can help us to find the volume of three-dimensional shapes by calculating the integral of the area of this region, okay? So let's split this into two parts here. So let's do orange for orange. So for part one, okay, we're rotating around the x-axis. So the formula for finding the volume would be the pi times the integral of, let's say this, of the radius squared, okay? So we're trying to find the area of these cross-sectional circles, right? Just in 2 dimensions, to calculate the area, you find the area, the small areas of each rectangle, and you sum them together. In 3-dimensional shapes, for this specific shape around the x-axis, we're finding the cross-sectional circles, and we're calculating these the sum of those small circles all added together to find the volume. Okay, and that's given by this formula here. The volume of the area, pi r squared, the integral of pi r squared, but I just factored out the pi, okay? All right, so for our other shape, so this is around the y-axis, okay? So for reasons I'm not going to get into because it's a very long description and explanation, we cannot calculate the cross-sectional circles of this shape. So instead, we're going to calculate cylinders, and we're going to add them all together. So we're going to find cylinders of small increments within the shape, and we're going to add them all together. So the volume for this kind of shape around the y-axis will be pi times the definite integral of the the radius and the height of the cylinder. Okay, so radius and height, okay? So that's how you calculate these two shapes. And this equation here is called the shell method, and this equation here is called the disk method, okay? And the method is dictated, the use of each method is dictated by how you rotate the region on which axis, okay? So the general rule of thumb, if you rotate around the y-axis, you use the shell method. If you rotate around the x-axis, you use the disk method. Okay. All right. So let's try to first of all calculate the area for each of these cross sections. Okay. So if we look at this shape here, and I'm going to look at this, the cross section is going to be determined by, or the area of this circle is going to be determined by its radius, right? So the radius is only determined by one thing, and it's determined by the function x. So you can see here that I didn't draw it really correctly because the x-axis is supposed to be going through here, but the radius, sorry, this is purple. The radius can be found from the x-axis, I guess, to the top, right? And that top, and this height is the y value equals to x squared. So our radius here is equal to x squared, right? So now we have found our radius, which is just pi of BA of x squared squared, okay? And now all we need to do is to find the bounds, and our bounds are from 2 to 0, okay? So these are our bounds here. So we're going to use those as for our interval. So we're going to calculate this integral here. The integral of x to the power of 4 from 2 to 0. Okay? Let's think about this integral now, okay? So if we're thinking about this integral, we need to find the radius and the height, okay? So the height of this cylinder, it really helps because I can't really draw this, but I'll show you on this one, okay? So this is the shell method, and they use a cylinder to calculate the volume of a region that's rotated around the y-axis, okay? So this is the function that they have here. So they recognize that the height of their cylinder is determined by the function itself, okay? So the height is here from the x-axis to here, and that is determined by this function. And the width is going to be determined by the origin from the center to where it touches the curve, which is x, okay? So in the same way, we're going to use that height and that radius, okay? So that means that this equals to pi times b of a. The radius is going to be x, and our height is going to be x squared, okay? So we're going to calculate this integral. X cubed, okay? And this is going to be 2 pi, sorry, because we're calculating the surface area. Yeah. Okay. So now that we have found our integrals, we can now calculate our integrals, okay? So let's start with our orange one first, our orange shape. All right, so this is equal to pi of 1 over 5, x5 to 0, okay? And that equals to pi of 2 to the power of 5 is 32 over 5. Yeah, 32 over 5. And that equals 32 over 5. Pi over 5, okay? So going to our purple shape here, we have our bounds here are also 2 and 0. So 2, 0, x cubed dx. And solving for this integral, we get 2 pi 1 over 4 x to the power of 4 of 2 and 0. And that equals to 2 to the power of 4 is 16 over 4, that's 4. So that's 8 pi. Okay. All right. So so that's how you calculate the integrals, or the volumes of these two unique shapes using the disk and the shell method, okay? And just again, for the disk method, we're calculating the sum of these cross-sectional circles, the areas of these cross-sectional circles. And to calculate for the shell method, we're calculating the sum of incrementally small cylinders, the surface area of those cylinders, okay? So these are the two equations, and those are dictated by which direction the region revolves around, either by the x-axis, which is the disk method, or the y-axis, which is going to be the shell method, okay? And calculating these integrals are easy. All right, so the junior tutor also did the same solution. Another rule of thumb, I guess you can use, is if the differential strip, all right, so if you're thinking about differentiating this two-dimensional figure, so you're differentiating it into rectangles, right, is perpendicular to the axis of rotation. So if you're thinking about rectangles, it's perpendicular to the x-axis. So when you rotate it, it's going to be perpendicular. Then you use the disk method, okay? But if the differential strip is parallel to the axis of rotation, so this rectangle is parallel to the y-axis, and you're rotating it this way, then you use the shell method. And this is more intuitively better to think about, because if you rotate a rectangle around a x-axis, you're going to get a circle, right? But if you rotate a rectangle around the y-axis, you're going to get a cylinder like this, right? In three-dimensional terms, I guess. So that's another way to think about it, okay? So these two solutions are correct. They just converted to cubic units, but but I did not do that. Okay, so this solution is correct. Good work and nice illustration. Okay, cool. All right, let's move on to question number 6 here. All right, so how do you differentiate y equals x to the power of x? Okay, so you can really just use your power rule here, but honestly, that's not going to give you anything of substantial of substance. So we're going to use implicit differentiation instead. Okay. So let's write this out. So y equals x to the power of x. So we're going to apply the natural logarithm to both sides. So ln of y equals ln of x to the power of x. According to the power rule of logarithms, you can move this exponent down. So this equals to ln of y equals x ln x. Okay. We're going to implicitly differentiate both sides. So d of dx of ln of y equals d of dx of x times ln of x. Okay. So the derivative of this is going to be 1 over y times dy over dx. And this one's going to be a chain rule, so we're going to get ln x plus x times 1 over x, which is just 1. Okay, cool. So isolating for dy over dx, we get y times ln x plus 1. Okay, and now y equals to x to the power of x, so we get x to the power of x times ln x plus 1. So that's our derivative. Okay, we use implicit differentiation, and then we sub back in y after we implicitly differentiate it. Okay. So this is also what the junior tutor did. They applied the natural logarithm to both sides, and they implicitly differentiated. And through that, they were able to find a derivative for x to the power of x. So the solution is correct. Good work. Okay. All right. Let's move on to question number 7. So what is the formula for the surface of a cylinder? Okay. Surface area. So a cylinder is basically has 2 circles at the top, and it has a surface that connects these 2 circles together. Okay, so this is what it kind of looks like. Sorry for my terrible drawing. This is what a cylinder looks like. Okay, so it technically has 3 sides. So we can break it up into these 2 circles and this huge long, I guess, area. So we can split it up into 2 circles, I guess you can say. So 2 circles. So, all right, 2 circles and a rectangle. Let's make this in yellow. Okay. Oh, whoops. All right. So a cylinder can be broken up into, oops, into oh, this is really big. Sorry about that. Let me change the thickness. Can be broken up into 2 circles and a rectangle. Okay, so we know what the area of these circles are. It's going to be area is going to be pi r squared for both of these. Right. But what about the width? Okay, so if we were to think about this, right? So the rectangle's length would be the height, right? So it would be the height of this rectangle, I guess. So length is here, and the oh, I should write h. And the width is going to be the circumference of these circles, okay? Because they kind of wrap around the whole circle. right? So if you were to unwrap it, it would be like a it would be the circumference, right? So it would be 2 pi r. Okay, cool. So now if we all add these together, so the surface area of a cylinder would equal to be the area of these two circles, so pi r squared plus pi r squared, plus the area of this rectangle, which is 2 pi r times h. Okay, and if we were to simplify this, would be 2 pi r squared plus 2 pi r h. And if we were to simplify this further, we get 2 pi r plus h. Okay, so that's the surface area of a cylinder. Okay, so this is also what the junior tutor got. They reasoned that the surface area is the area of these two circles and the area of the lateral surface, I guess you can say. They found out that the area of the base is just pi r squared. They times that by 2 because there's also a top. And then they reasoned that the width of the rectangle or the lateral is the circumference of the circles. And because of that, the area will be the height times the circumference of the circles. And then they added it all together. So the solution is correct. Good work. Cool. All right. So that wraps up today's lesson. I hope that you guys learned a lot today about calculus and about integrals, and specifically about calculating the lengths and the areas of curves and shapes by using integrals. So if you have any other problems with your calculus or your calculus, with any tests or any homework with that, please submit them through OneClass. Other than that, I hope you guys have a good evening, and I'll see you guys next time.